Press.
Okay. So we look at have a PowerPoint happening here. We look at independent sample mean today, and I will do that as a review. Okay. So just a quick rundown. I think I have you on the next slide. The key formula, the central formula. So what I want to do is to kind of go through this, starting from one sample from chapter 8. So that we will have everything in one place. Let's get a new. Let's get a free slide. Okay, so in all this, as we are going on, you see that the central thing is the test statistics, right? And this is the formula we have here for independent samples. Okay. But just as a quick review, how we got to this point, in chapter 8, we were dealing with one sample. So this would be a situation where you are given a population mean. All right. So let's say, for example, let's say, for example, we are comparing blood sugar level of a sample of people with those in the population. So let's say in the population, the blood sugar level we use as initials to say blood sugar level will be, let's say 90. I think it's measured in milligram per deciliter or something like that. That doesn't matter. So it's 9. Let's use this as the population value. So assuming this is the population value, and I'm trying to recover what we did in chapter 8, right? I mean in unit 8, right? So assuming this is a population value and you're asked to take a sample, just one sample, and compare that with that. So let's assume somebody is making a claim that on the average in the population, everybody's blood sugar level normally should be 90 milligrams per deciliter, right? And then you're trying to verify whether that claim is true. You're ideally going to take a sample of people and then find their details, their statistics. So let's try to do something like that. So the first thing to do is to kind of state the hypothesis. Okay. So here, let's say this individual is stating that the null is that in the population, the average blood sugar level should be 90 milligrams per deciliter. Right? Okay. So you want to dispute this claim from 3 angles, right? There have to be 3 ways to do that. H1 could be that, hey, the population mean is less than that, right? Another way to do that is to claim that population mean. So these are all alternatives, right? That population mean is actually greater than that. A third way to approach that is to say, hey, the population mean is not equal to that. Okay. So these are 3 possible claims, but how do we know which one applies to a given question? Just read through the question, right, and try to see what it's saying. And from there, you can pick up this information. Okay. So that's your hypothesis statement. And again, I'm reviewing what we did in unit 8, one sample mean. So if this is what we've gotten to, the next thing will be to probably develop the test statistics. So let's go to the next page. I'll put this as well. Any question on stating the hypothesis? Again, this is a review for one sample mean. So let's go to the next page and develop the test statistics. So what we do then is just, okay, I want to verify this claim. Then you're going to take a sample data, right? And then from that sample data, you're going to get your statistics. And the statistics you need is just the mean, sample mean. Okay, let's assume in the sample mean, you took a number of people and measured their blood sugar level and you got, let's say 92. Okay, milligram per deciliter. So the question is, if this is what I got from my sample, is that person telling the truth who said it's 90? Is that the truth, right? It could be either way. You know, the person could claim that the sample you took happened to people with slightly higher blood sugar level than the normal population. You know, and a lot of things could happen. So let's say we got this, then what we need to do to test that hypothesis is to construct a test statistic. Right? Again, I am reviewing unit 8. One sample mean. So here the test statistics will be compare that mean you got from the sample to the claim. Right? And then divide it by the standard error. And I want to emphasize that today. I don't think I've been doing that. So this formula, the test statistics, has a pattern, and this is going to go across. And that's what I'm trying to show you today. The test statistics is the difference in mean divided by the standard error. Okay, that is the general pattern. So what we have here in the numerator is just the difference in mean between the sample and the claim, and at the bottom is standard error. And if I should go to where we pick that standard error very quickly, I think it's in unit 7. Okay, it should be in this section. It's a central limit theorem, I believe. Yeah, so it should be here, unit 6. Okay, maybe I don't have the PowerPoint, sorry, but I thought I do. I did right now. Okay. Okay, somehow I can't see that here, but I thought I had that this morning. Let me check the download bar. I just wanted to show you the connection between these things so that it will make some more complete sense. Okay, yeah. So when we worked on this, that was in chapter 6 in central limit theory. Remember when we made this simulation and we showed that this is the adjustment you need to make if you have a sample size that is small. Right? That is where what we are picking from. This is actually a standard error. That is what we are picking to divide in that test statistics. Okay, so if we go back there. So the bottom here is the standard error, right? And the top is the difference in mean. This pattern is going to hold true for all the test statistics as we move forward. Okay. So this is the formula we use for test statistics for one sample mean. So here, this is your sample mean, right? And then you're comparing that to the population claim. This one sample. Okay, so beyond this in 9.1, we went to 2 samples. So in this case, this would be like a situation where somebody is trying to verify, compare 2 samples. So let's say, for example, I'm going to compare heart rates before and after exercise. Okay. Maybe ERSCIS. So heart rate before and after exercise. The idea here is that you have two samples, right? But they are coming from set of the same individual. Right? So if you, let's say we pick everybody in class now and take your heart rate right now and give us some kind of exercise and take our heart rate again. We're going to have a paired data. So two heart rates from every one of us, right? Okay, so the hypothesis statement here will go this way. The null here will be that we are comparing the heart rate we took before, let me use a B here, with the heart rate we took after. Okay, but these two are coming from the same individual, so they are kind of paired, right? Okay, I will make that argument later. So I could go ahead and dispute this in three different ways, right? We could say the null is that the heart rate of the first group is greater than the heart rate of the second group. That would be one claim. Another claim could be, sorry, this should be H1, right? Another claim could be that the heart rate for the before the exercise is less than the heart rate after the exercise. The average heart rate among the persons. And a third claim could be that heart rate is not equal to, right? So the person making this third claim is not taking a position as to greater than or less than, right? Okay, so if I have all this in place, I could go ahead and rewrite this still. Take note that both data A and data B are taken from the same set of individuals, right? So I don't really have two different samples. I actually have two samples from the same person, same set of people. So I could decide to say, okay, why not just ignore this subscript, right? Let's keep it in place for now. I could decide to rewrite this. Let me use a different color. I could decide to rewrite what I have here as H naught as mu before minus mu after is equal to 0, right? And that makes sense because if mu before and mu after are equal, according to this statement here, then if I subtract from each other, I get 0. Right? So this is a different way of writing the null hypothesis. Okay, then I'll go ahead and rewrite the alternative also that way. So let's get another page here. So here we've just stated the null as mu before minus mu after. This should give me 0, right? If that is true, if the two are equal. Okay. The alternative could be written also, right? On the other page, we had that the alternative as mu before greater than mu after, right? This could be rewritten as mu before minus mu after. If this is true, if the mean before is actually bigger than the mean after, then when you subtract this, the value you get should be more than 0, right? So that is one way. And if we follow the second claim, the second alternative claim is that mu before, the heart rate before, is less than the heart rate after, which is the likely thing you expect, right? If this claim is true, then this can also be written as mu before minus mu after. If this is true, if mu before, the average heart rate before, is actually less than the average heart rate after, then your results here should be less than 0. Right? Hope you're following the trend. And then finally, let me put it over here. The last claim is that H1 it could be that the heart rate before is not equal to the heart rate after. That is what this person is claiming. Right? If that's what this person is claiming, then you could write this as the heart rate before minus the heart rate after is not equal to 0. Okay, so these are all three ways of writing the same thing. But for your homeworks, as you may have seen on the video, there's a different way to we want you to write this, and let's summarize that here first. So let's take it to green. So let's, for example, remember that if this is paired test, right? Okay, so what we're covering now is in 9.1. Right, I'm trying to review from 9.8 going down to where we are today. So this is paired test. So remember that in this instance, this value, the heart rate before and the heart rate after, is taken from the same individual, right? So I can as well rewrite this as, maybe if I remove the notation, since I'm talking about the same individual, I could rewrite this as H1 being equal to, let's call that individual I, the heart rate is also equal to, okay, so I'm using the second one now, right? The heart rate, let's write it as individual I, heart rate minus the same person's heart rate is not equal to 0. For example, if I'm trying to rewrite it. Okay, so what I'm trying to make here is that we can actually remove this and put a simple unit there to make it simple because we are dealing with the same individual. So for that reason, I could actually have written H1 as simply the difference in the heart rate, but that's what I'm doing. The heart rate before minus the heart rate after. So I'm looking for the difference between them. So I could say UD, representing the mean of the difference, is not equal to 0. Right? So if I do this for all of them, then I have an entirely different way of stating the null and alternative hypothesis. So essentially, I'm trying to replace every place I have mu, mu before minus mu after. I'm trying to replace that with mu d, right? So let's rewrite all of this in the next slide. So if I do that, then remember what I'm trying to do now is to replace mu1, or let's keep it as mu b minus mu a, the heart rate before, and if this is the null hypothesis, we are saying this is less than, it's equal to 0, right? I'm trying to replace this one here with mu d. If I do that, then the hypothesis could be written as mu naught is such that mean of the difference is equal to 0. So this would be my null hypothesis. And for the alternative hypothesis, I will have that H1 is that mu d is, let's write that better. So that is a subscript. Alternative will be that H1 is that mean of the difference is less than 0. Okay, that's one way to look at it. And this will be true if the heart rate before is smaller than the heart rate after. All right, so if this is true, if I subtract this, I should get less than 0. Another alternative would be that mu d is greater than 0. Right? And then a final one, and this will happen if the heart rate before is bigger than the heart rate after. So if I subtract this, I'll get a value bigger than 0. And the last one is that mu d is not equal to 0. This will be the last way to state that. Okay. So that was what you saw in the video last class, right? That is paired sample. So you want to go back and look at that again if what I've stated here is not there. So this is the way you're supposed to place your answer on the assessment, right? Because we are dealing with paired sample. We know that these samples are paired, or you can say matched. They are coming from the same individual, heart rate before and heart rate after. And it could be any of the before and after kind of data from any other kind of illustration. Okay. Okay, so and we went ahead to say, okay, what about the test statistics for this? What will it look like? Okay. And I think I should get a page and keep this side by side so that you can easily compare that. We can easily see that together at the end of the day. So let me say here, make this portrait. Okay. So far, we've seen the one sample scenario. We're looking at the paired sample at the moment. All right, paired or matched. And we're going to look at independent, which is our focus today. All right. Okay. So over here, we saw that the test statistics here was given as the sample mean minus the population mean divided by the standard error, which is this. All right. So in this case, so in this instance, we are going to be using this, right, to make our representation in the test statistics. So let's explain that here, and we'll take a notes over there. So since we are using mu-d now as our focus, so our test statistics will also be written in that term. Our test statistics here will be mu-d, the mean of the difference, minus 0 divided by also the standard error. And the standard error we're going to be using here, standard deviation of the difference. Okay. Again, you see details of this in the video. All right. So you see the similarities between this and the other one, but because you're subtracting 0, you can simply write this as mu-d divided by standard deviation all over square root of n. Right? Remember what mu-d is, so you can actually expand it a little bit. So if you expand it, then the test statistics is something as mu before minus mu after, if you're doing before and after, divided by standard deviation of the difference over square root of n. All right, so this is just the standard version, but we are going to kind of try to focus on this one because this is simpler, right? Okay, so let me take it over to that other page and have a simple formula written also. So over here in the middle, we know that for match pair, our test statistics, t-test, is going to be mean of the difference divided by standard deviation of the difference all over square root of n. Right? Okay, so and you saw in the video, you get the difference and then find the mean, right? But over here today, we are assuming that the data are not really related. Like data are kind of independent from each other. Okay. So that this combination we did here, right? The way we turned this into mu-d is not possible. We did that because they are coming from the same individual, right? So if I have two different samples, my formulas or my work should look this way. So for today, we are dealing with independent samples. Okay. Independent sample. So if I'm dealing with independent sample, such that the data are not related, then my null hypothesis will still be stated the same way as the paired case, right? So let's say I have data of group 1 and I'm comparing that to data of group 2, right? Okay, so there are three things I could do on the alternative. On the alternative hypothesis, I could claim that the group 1 mean is less than the group 2 mean. Right? I could also claim that the group 2 mean is greater than the group 1. The group 1 mean is greater than the group 2 mean, right? And eventually, lastly, I could claim that I don't know which is greater or less, right? So we had the same thing on the paired sample case, right? Remember over here? Okay, maybe move one step more. We had the same thing on the paired sample case, just like this, but we were able to summarize that and make it one like this ones. We replace those combination with UD because we are looking at pairs. But in this case, in the independent situation, these two are coming from two different populations. This will be like class A and class B. So you can't really combine them, right? So you just let them have it remain the way it is. So this is our final work setting our alternative and null hypothesis in the dependent sample case, which is what we're looking at today. Okay. So how do we write the test statistics for this scenario? So again, you are dealing with two samples, right? And remember the general formula for our test statistic. Our test stat is difference in mean divided by standard error. Right? Okay, so now you have two samples, right? Mean of group 1 and mean of group 2. Our test statistics follow that pattern, right? So your test statistics will be the difference in the mean. So we're dealing with sample mean first. Sorry. So you're taking a sample, you have the difference in those two samples. You're comparing this, right? You're comparing this with the population, right? Remember, if we go all the way back here at the beginning today, we're comparing, you have a population here, and you're comparing the mean with that population. But in this case, the population value was given to you and dealing with only one sample, right? But where we are right now, dealing with two samples that are independent. We are comparing our mean with the population mean of those two groups. Okay. And we're dividing this by the standard error. In the one sample case, our standard error was just standard deviation divided by square root of n because we had only one sample. In this case, we had two. So we're going to try to write the same similar thing. We're going to write standard deviation for group 1 divided by square root of n for group 1 because we are not dealing with two samples, plus standard deviation for group 2 divided by n of group 2, because now we're dealing with two samples, right? So you see, this is an exact mirror of what we were doing before in one sample case, but you just added the fact that you had two samples and then you have that added in the formula. Okay? But if you go to the text, this was written slightly differently. And I will do that on this page. So what I've just written on the board is that the t-test for this, if you're dealing with two samples, is the mean of group 1 minus the mean of group 2, right? Minus the population mean of group 1 minus population mean of group 2 divided by their standard error. Okay. So divided by standard error of standard deviation of group 1 divided by square root of n of group 1 plus standard deviation of group 2 divided by square root of n of group 2, right? But I can rewrite this formula a little bit. And you could use this totally right, but in some tests, you're going to see something slightly different, but they are technically the same thing. So I'm going to have the mean of group 1 minus the mean of group 2, and I'm trying to find the difference between that with the mean of group 1, population mean of group 1, population mean of group 2. But under it here, I could put in square root here. Because I put in square root there, then I'm going to ignore the square root on the denominator, but I have to square the numerator. Okay, and if you think about that algebraically, you see that it's true, right? So that is how we got that formula on the text there. So this is divided by n1 plus the square of n2 divided by n2. Okay, these two formulas are the same, right? If you take the square root of the numerator, so the numerator here is the variance, right? If you take the square root of the variance, you're going to get the standard deviation, right? And then you just keep the square root of the denominator. So whichever of the two you use, that'll be fine. I think the text cites the second one. But one more thing I will add, one more layer I will add on this is that we can simplify this formula further, right? We can simplify it as, let me use green. If the null is true, right? If the null is true, and what is the null? The null is that mu of group 1 is equal to mu of group 2. If this is true, then it will imply that mu of group 1 minus mu of group 2 will give us 0, right? Because if those two are equal, if you subtract, then you should get 0. Okay, so if this all I've said here is true, then we can simplify this formula. Just replace this one here, because we just saw that this is 0. And replace this with 0, right? So writing over here, the modified formula for independent t-test will then be written as the t-test will be equal to x bar 1 minus x bar 2 all over square root of standard variance of group 1 all over n1 plus variance of group 2 okay, let me write that well. I don't want to do that. Hold on. Okay. As variance of group 2, right? So I could write that formula that way. So eventually I will try in this class to be using this one, right? But what I'm trying to show you is, have a conceptual understanding of all these things so that if in a question you are given the variance, which is just the S standard deviation raised to the power of 2, then you could use this one straight, right? If you are given the standard deviation, then you could use this one, right? It doesn't matter. You can change from both sides. Even if you're giving standard deviation, you can actually square it to bring it down to standard formula. Okay. But take note of the uniformity, and I will do it in one more page because I want you to have clarity on this. So that when on the assessment, you're going to get a question. Nobody will tell you it's one sample. The question you won't see that it's two sample. I mean, okay, you will see that it's one sample or two sample, and you will see whether it's matched pair or independent pair. You're going to make that decision from the question, right? But see the similarities between all of them. In all the test statistics, we construct it by finding the difference in mean and divided by standard error. This is the general formula. So you now go in and fit in what is required in each case. So just a quick recap again before we start solving abstract question. In one sample case, right, we saw this in unit 8. Here, the test statistics is the mean of the difference, and we had only one sample, right? So we are comparing, right? So one sample compared to the population mean. So that difference on the numerator divided by the standard error. Standard error is standard deviation divided by square root of n, right? And if we move on to the matched pair, or you can call this dependent, right? I explained all that in the video if you watched it. Dependent pair, yeah. If we move over to that scenario, here we have two samples, but they are matched, they are dependent. Our test statistics is the mean of that difference, right? Divided by The standard deviation of the difference all over square root of n. Okay, so again, on the top is the difference in mean. That's what you see up on the top, all over standard error. And then we are dealing today with independent t-test, right? It is still a two sample, right? You still have two samples here, but they are independent. They are not dependent on each other, so we keep them separate. So you see that your test start is still the same thing. On the numerator, you're still going to look for the difference in mean. So here we have group 1 minus group 2 mean. Because they are different, I'm going to keep it different, right? Divided by the square root of variance of group 1 plus the variance of group 2. Right? So if you understand this naturally this way, that is one thing to distinguish in the assessment, right? And then the second thing you want to distinguish is now whether it is one pair, or one tail, or two tail, or right tail, or left tail, right? And then you begin to make your decisions about how to solve them, whether you're going to use Z or whether you're going to use T. Okay? All right, but I wanted to show you that these are all following a pattern. Find the difference of mean on top and do the standard error below. Okay? Any question at this time? Okay, we're going to go ahead and solve some concrete example in this section. I have this posted under section 9, under unit 9. Let's close out this. So it's over here on unit 9, right? You can open that or just follow through what you have. So here is a situation like that. Shoppers at the mall spend more money on average the day after Thanksgiving compared to the day after Christmas. So we're going to get two samples. One was the results after Thanksgiving. The other one was the results after Christmas. In your thinking, would you think these two samples are matched? Are they dependent? Right? And by dependent, we mean something like, for example, like the example we gave in this earlier today. If I measure your heart rate right now, ask you to do some kind of exercise, and I measure your heart rate all over again, I'm going to get two sets of data. And those two sets of data are coming from the same set of individuals. So you see, they are related, they are matched, right? So in this scenario, do you think you have a match pair here? Just think through it in your own way. And this is the mental exercise you'll be doing while you're writing the assessment, right? And I hope you practice that on the homework. But the homework is in sections. So if you are dealing with one sample, you know it's one sample. If you're dealing with match pair like we did over the video, you know it's match pair. If you're doing with independent sample as we're going to do today, you know. But so that is in section, right? But you should have the practice of what if I just see the question, I don't know the section is coming from. How do I determine how to approach it? Right? It's critical to being able to do that. So tell me what you think. Do you think this is the data I'm going to get from shoppers on Thanksgiving and the data I'm going to get from shoppers a day after Christmas? Do you think those two data will be matched? Or would they be independent? And what would be your reason? And don't make it correct. I just want to get somebody say something that is the typical thing that will happen, right? So if whether your answer is right or wrong, it will be the same thing that many people are going to be getting. So whatever answer you give, there should be at least 2, 3, 4 persons in the class who will think the same way, right? So if it is right, fine. If it is wrong, also fine at the same time. It doesn't matter.
Independent because they're two separate days and like holidays and like just
okay. So independent. Okay. So independent because they're just two separate days. two separate holidays. So we don't think that what happened in both of them should be similar. Okay, do anybody have contrary reason?
I agree with him because there's no correlation between the two being that they are separate, so.
Okay, but say something more like, what would be your reason for saying that they are not?
Well, they're two
related?
different like days after a holiday, like one's after Thanksgiving and then one's after Christmas.
Okay. And that is also good, right? Do we get anybody say something different? Anybody has a different opinion from these two? Right? What if I say that I have a set of people that shopped during after Thanksgiving? I collected their data and I get the same set of people to go and shop after Christmas and also collect their data. Would that still be independent? Right?
You're saying like you got the same shoppers for it?
Yeah, for a day after Thanksgiving and a day after Christmas. Would the two still be independent of each other? So one logic here is that even though it's same set of people, it's different days, right? Different holidays. So their behavior could still be different, right? The data could still be different. The other logic is that these are the same human beings that are shopping these 2 days. So likely also their shopping pattern could also be the same, be similar, right? It wouldn't change if these are happening the same year, right? So what I'm trying to make you think about, and the answers you all gave in the first one, Collins and Brenda, those 2 answers are correct, right? Those 2 are independent because they are 2 different holidays and there is nothing in the question telling you these are the same shoppers. So if I have 2 different holidays and I have 2 different sets of people who go to shop, there is no way the data could be related, right? Okay, so but I want you to pay attention. So if I tweak that a little bit, I say the same set of shopper shopped before Thanksgiving and after Christmas. I mean, after Thanksgiving and after Christmas, if it's the same, then I'm giving you reason to believe that they are dependent, right? Okay, so watch out for such little tweak in your assessment. So that way you could actually determine. So once you determine what to do, let's say they are the independent, as in this case, then you go ahead and answer the same set of questions that we answered in one sample case and that we answered in in the match pair, right? Okay. So let's look at the first question. It says, for this study, we should use, okay, so you want to drop down this arrow and there are a couple of scenarios. Based on what you did here, you should be able to pick up the right one, right? So here we know that these are different, there is a t-test between 2 independent populations. Because we know that those 2 groups are totally different from each other, okay? Then we look at the second one. The second part of the question is the null hypothesis. The null hypothesis here, I mean, I have this answer key written out here, but again, you pay attention to what it is. The null hypothesis don't normally change. It's going to always be comparing with equality sign, right? And the alternative hypothesis will be based on what the question is saying. So in this question, it's saying shoppers are the most spend more money after Thanksgiving than they do after Christmas, right? That is giving you idea of greater than more, isn't it? So, and that is why you see that the alternative hypothesis highlights that group 1 is greater than group 2. Which should be group 1, which should be group 2. Whichever is mentioned first should be your group 1, whichever is mentioned second should be your group 2, right? And then you look at the question and say, is he saying more? Is he saying less? Is he saying not equal to, like different or the same? So that means this. But I believe you've got enough practice on this already. So let's go to starting question. Now, what is the t-test? The t-test, we've seen that the formula is given as the difference in the mean divided by the square root of the variance all over N1 plus the variance all over N2. Right? The variance of the second group all over the sample size for that. Okay, so we go ahead and plug in. The rest is just plugging in. So you see that the bulk of the work is making these decisions that we are making here, deciding on how to approach the question. Once we've made that decision, you are more or less done. Okay? So let's plug in the values. From this question, we have that the mean, let's have it somewhere here. We have that the mean sample mean for group 1 is 122. And we have that the sample mean for group 2 is 34. It's 120. And we have the standard deviation for group 1 is 34. And the standard deviation for group 2 is 42. Right? So these are the data we have, and we have that alpha is equal to 0.1. Right? This is what we can pick from the question. And then we'll go ahead and plug in here. So solving here, our t-test will just be the mean of group 1, 122, minus the mean of group 2, 120, divided by the square roots. So what I have here is standard deviation. So if I'm going to use this formula, then I have to square this, right? So this will be 34 raised to the power of 2 divided by n for group 1. Okay, we didn't pick that up. Let's pick the values of n. It says here 55 persons were randomly, shoppers were randomly selected for the Thanksgiving holiday. And 50 persons were randomly selected for the Christmas. Okay, so we have 55 and 50. So here we know that N1 is 55 and N2 is 50. Okay. So we continue plugging in. So over here we have divided by 55, right? Plus 42, the standard deviation, but we are looking for the variance here. We square that, and we're dividing that by 50. Any question? I would suggest do this slowly, do it in parts, one at a time, right? So if I subtract the numerator, it's clearly 2. That would be easy to handle. Yeah, let's go ahead and do the denominator. Okay. Let's first of all get what the value of 34 raised to the power of 2 divided by 55 is. And then we'll have it down plus 42 raised to the power of 2 divided by 50. So if you get an answer, let us know. And let's have maybe 2 people compare.
Just what, do you just want what's under the square root?
Yes, but just on what is under it, but let's do it in parts, right? Let's do 34 raised to the power of 2 divided by 55 first. Let's have that on one side and add the other part.
I got 21.0181.
21.0181.
I got 8 too, but I got the same thing.
Oh yeah, that rounds fine.
Okay. Okay. Okay, so 21.0182. Yeah, okay, thank you. 21.0182. And we are going to add the other part of it, 42 raised to the power of 2 divided by 50.
35.28.
35.
I got that too.
Okay, thank you. Can we make it 4 digits?
That's all there is.
Okay, so others want as 0. Okay, so we can actually write it here then. So we go ahead and divide. Right? That's true. Okay, let me just scratch it out. So go ahead and sum this up and take the square root and divide with 2. Can we get a final answer? Let me write it over here. The square root of 21.082 plus 35.28. So we divide that, we divide 2 with that one. Yes, please.
Can you read the numbers that are underneath the square root line?
Say that again.
Can you read like the 21 point? I just can't read the number.
Oh, okay. On this side, right?
Yeah.
Okay, so I actually relate it actually. So but that is 21.0182. 21.0182 plus 35.28.
Thank you.
This is not very sensitive. Okay, anybody got an answer for that?
I got 0.2666.
Okay, so when this is summarized, you got 0.2666. The fourth digit, do you know what it is?
That is 4 digits.
Okay, so it's this way, 0.2666. Okay, thank you. Anybody else got something different from this one?
I got the same thing.
The same thing. So, of course, if you run this off, you get the same thing as we have here, the 3 digits. Fine. Okay, so we'll go ahead and do the p-value. I'll be the next. Can we do this on a cell? So you see, these things are more or less the same. There's still nothing new, per se, but you want to take note of the type of test you're doing. Okay, so in this test, is this 1-tailed test or 2-tailed test?
1.
1, right? So greater than, less than is 1, right? So let's look at that. So you have your T dot distribution. Okay. So we use right tail, and we're using that will imply. So if you have this like this, and you're focusing on using right tail, and I explained this last slide, it's technically the same thing as if you have a left tail. In this case, we have a right tail, so we're using that. But whether you have a left or a right tail, if you're plugging into this formula, just make it positive, right? That's what makes the difference. So if this is 5%, and this is 5%, the area of your interest will be the same, whether it is on the right or the left, if they are the same proportion. Okay, so we go ahead and put in our test statistics. Is the right tail, so I think the positive one, but even if it's left tail, also do the positive one. So here we have 0.2666, and let's use those for the 0.2666. And you look at the degree of freedom. Okay, so one thing I didn't mention when I was doing this overall review is the degree of freedom. I think this is a good time to add it. So the degree of freedom for one sample case is n-1. Hope you recall that, right? The degree of freedom for match pair, because they are matched, is also n-1. But the degree of freedom for the independent pair, because there are 2 of them, not matched, they are separate, then you just add the 2 groups and subtract 2, right? So that is just like, essentially, if you do the algebra here, this is like n-1 for group 1 plus n-1 for group 2, right? If you simplify this, you end up with, opening up the brackets, you have this, Right? If you work this further, then this is just n1 plus n2 minus 2. All right, so you see how similar these things are. So this is your degree of freedom that we use here. So because we are doing a t-test, we know we're going to be using a degree of freedom here. Now, in this question, let's go back to it for clarity. In this question, we have first group is 55, right? And the second group is 50. So if you add those two together, you're going to be getting 105 as your total sample. And then, of course, you remove 2. All right, so your DF, put it down here. So your degree of freedom, which is n1 plus n2 minus 2, will be 105 minus 2, which will give you 105. All right? Okay, so on the Excel formula, remember what you put in there is in your t dots dist. If you're doing one tail, then we're using right tail. What you put in is your test stats, comma, the degree of freedom, right? Okay, so let's go ahead and finish it up. So we have our test statistics already, then the degree of freedom is 103. And you press your enter key, and you have your p-value. So here we have that the p-value is 0.395155. So we have here 0.395155, right? And if you round up, of course, you have the same as the answer that we have on the. Okay. Any questions so far? Let's move up and speed up a little bit. So if you compare your p-value with alpha, remember your alpha is 0.01. Right? If you compare those two, you see that the p-value is of course bigger. So we know that the p-value is greater than alpha in this case. And of course, if it's greater, I believe you've got enough practice on that one. If it's greater, what do? You reject or fail to reject the null hypothesis. Okay. If you're not comfortable with that, be sure to review that. Okay? So fail to reject the null hypothesis. If it is less, you reject, right? And then you could answer the next question. You want to read through that carefully. But maybe for explanation, let's say generally, if p-value is less than alpha, then we say the result is significant. Okay, but if p-value is greater than alpha, then we say the result is not significant. How else can you say not significant? You can also say insignificant. So watch out for this interpretation, and it will help you eliminate the options very quickly, right? So here the p-value is bigger than alpha, so we know our result is not significant. So if I look over here, this one says statistically significant. I am taking that off, but I would say to read everything, right? I'm trying to speed this up so that will save time. Read all through to be sure that it is saying the wrong thing, but apparently this is saying the result is statistically significant. It is not in this case because we got the second value, right? We got this name. So if you look at 1 and 2, let's go through that very quickly. The results are statistically significant at alpha 0.1. So there is statistically significant evidence to conclude that the population mean amount of money the day after Thanksgiving and the day after Christmas are equal. Okay, so this is really saying something that is contradictory. So if you say statistically significant, right? If it's statistically significant, then you're going to reject the null. Oh, statistically insignificant, you're going to fail to reject the null. And if you fail to reject the null, it means you're retaining the null. And what is the null? The null is that H naught of mu1 is equal to mu2, right? So if we return the null, then we have evidence. We don't have enough evidence to support the alternative, right? So if this is insignificant, it means there is not enough evidence to support the alternative. Let's see. So the second one says the result are statistically insignificant at alpha 0.1. So there is insufficient evidence to conclude that the population mean amount of money the day after Thanksgiving shopper is more, right, than the amount of money spent after Christmas. So this will be more correct, right? Because we don't have enough evidence to support that alternative. The alternative says H1 says mu of after Thanksgiving is greater than mu of after Christmas. But we did not reject the null. The null says that they are equal. So you just try to pick this answer based on your results. Just look for something that matches, that agrees with what you got. And that will be how the result is. Any question or concern about this? Okay, so the next thing here will be a question like this one. It's also exactly the same thing as the one we just did, right? But the difference is that you're given a set of data, and that will limit this to maybe 3 or 4 data points, so you can walk through it easily. But by now, I want to believe everybody here should be able to calculate these statistics from data, right? You should be able to find the mean and should be able to find the standard deviation from a given set of data. Okay, so once you have those values, then you go ahead and then answer your questions. Yeah, so of course, when you drop down the arrow, this should be easy to select, right? Because let's look at this scenario. Do men score lower on average compared to women on their statistics finals? Okay. Final exam scores of 13 randomly selected male statistics students and 13 randomly selected female statistics students are shown below. Okay, so the question is, do men score lower than women? And we're going to just go through this very quickly. So the first thing you're supposed to do is to calculate your mean and standard deviation from your data, because you need that eventually, right? You need it to do your test statistics. And we are comparing 2 different groups. They are not the same, male, female. Like there's no indication that they are coming from anything that makes them related, in any way. So, but if I talk about twins, for example, I say a set of twins. There could be different gender, but at the same time, because they are twins, there is some kind of relationship, right? So that might become a dependent sample or a paired sample. Yes, please.
If it's giving us the standard deviation, why are we using T instead of Z?
It's not giving, so, okay, so in 2 ways. One is, it's not giving, you have not been given the standard deviation. You see, I highlighted it in yellow. I computed that. I expect you to compute them from here.
But in the one before, we were given the standard deviation in the question.
Yes, and so what is your question then?
So why did we use T instead of Z?
When do we use T?
When you don't have standard deviation,
When do you use Z?
when you have standard deviation.
Okay, so have you seen the video on 9.1?
Yes.
Okay, look at it very closely again, but who can answer that question better? Yes?
For Z, use population.
Use population standard deviation, right? We've emphasized this more than 3 times in the class, and I repeated in the video several times. Population standard deviation, not just standard deviation, right? Okay, so that's what we used to on that first one. And here, we are not giving, I am the one that have them in yellow. I just highlighted that so that you could, but I was making a statement that by now everybody should be able to compute that from here. Okay, so let's go ahead and walk through this very quickly. If you have computed that from this place, you have these 2 values, and then you go ahead and answer the question just the same way. Right? I'm going to skip these 2, but I want to believe you are able to see this one from the question. right? You're able to see that, say lower, so we know it's less. So let's look at the test statistics very quickly. Mean of group 1 minus mean of group 2 divided by the square roots of their variance. So we have that, and we are taking it for granted. We already have this value. We computed them from here already, right? And again, I believe we all should be able to do that. There are videos in unit 7 and 8 that has that calculated several times. So we want to save time. Okay, so if I'm picking up those values, maybe we should do this here. If I'm picking up the values here, let's plug in very quickly. So our t-test will be equal to the mean of group 1, which is 76.9231 minus the mean of group 2, which is 81.3846, all over square root of the variance, right? So you have for group 1, 11.8635. You are raising that to the power of 2 divided by the sample size. In this question, we are told 13 was randomly selected for both male and female, right? Okay, so you have 13 here. Plus the same thing here, 12.6527 raised to the power of 2 divided by 13 also, right? So if we simplify that, and we walked through that just a moment ago, if you simplify that carefully, you should be able to match this answer, right? And I just want to repeat the process of getting the p-value here with the time we have left. You have a question?
Yeah, so on your yellow calculations, if that's the standard deviation, later when you plug them in, why is it the variance?
So you're plugging it in as the variance, right? You know, in the formula you have S squared. So this is variance, right? So because you're taking that standard deviation and you're squaring it. Okay. All right. So I will complete this on my own and post it online. So you can also pick up that and compare it. But this is exactly the same thing we did on the first example. So you don't really have any new things to work on. Okay. All right. Please mark on the attendance before you leave.
Your sweatshirt's cute.
Which is.
Oh.